Minute answer questions are quick tests of your understanding of conceptual content in the chapter. If you're here to check on the answer to a particular minute answer question, skip around in the video and watch for the number to come up in the bottom left-hand side of the screen, because we're going to take this from the top. Let's take a look. First question. Does a moving average forecast become more or less responsive to changes in data series when more data points are included in the average? Let's see, more data points included in the average is a longer moving average. Longer moving average is less responsive. We remember that the longer the moving average, more data points, the less responsive the forecast. The shorter the moving average, the more responsive the forecast. Okay, next question. Does an exponential smoothing forecast become more or less responsive to changes in a data series when its alpha is increased? Increase its alpha, it becomes more responsive. We remember that the smaller the alpha, the less responsive the forecast, or smoother the forecast. The larger the alpha, the more responsive the forecast. Okay, good. Next question. If a forecast is too high when compared to the actual outcome, will that forecast error be positive or negative? Answer, negative. An important thing to remember, because error is actual minus forecast by definition. So if the forecast is too high relative to the actual, that's going to come out negative. Okay, good. Next question. Are quantitative forecasting models generally used for shorter term or for longer term decision making when compared to qualitative? Okay, quantitative uses data, qualitative uses human intuition. The answer is the quantitative are generally used for shorter term. You say, okay, why? Oh, because quantitative uses data. You have to have good quality data. Just generally speaking, you are more likely to have good quality data if you're talking about more the shorter term than like years and years out, right? If you're talking about years and years out, that's where you generally start to use more qualitative techniques. Next question. What do quantitative forecasting techniques require, in the absence of which makes them ineffective tools for predicting the future? We were just talking about that. That is relevant past data. You can't use a quantitative technique unless you have data to plug into it. You need past data, and I put relevant because this is important. The past data that you have has to be relevant to the future, right? You say, well, why would it not be relevant to the future? Well, there's things that could interfere with that, like you have past data on the sales of some certain model of something, but the new model just came out. I don't think that past data is going to tell you much about the future of the old model. Okay, anyway, next question. In time series analysis, any pattern that regularly repeats itself, a pattern, and is constant in length is referred to as what? That is definitional. That is describing a seasonal pattern. A pattern that regularly repeats itself and there's a particular interval, like within every year or within every month. We call that condition seasonality. All right, next question. The use of which alpha would result in a smoother forecast? Alpha equal 0.2 or alpha equal 0.5? Smoother would be alpha equal 0.2. Why? Because it's the smaller of the two, and the smaller the alpha, the smoother the forecast. The larger the alpha, the more responsive the forecast. All right, next question. A forecasting technique that takes the previous forecast and adds some percentage of the previous forecast error is called what? That is a verbal description of exponential smoothing. Simple exponential smoothing. Because think of the formula. You create a forecast by taking the previous forecast and adding some percentage. That's actually what alpha is. It's a percent of the previous forecast's error, which error is actual minus forecast. So that question just described the formula verbally. Good. Next question. Which forecasting technique is more qualitative? The Delphi method or linear regression? Oh, easy. Delphi method. Delphi method is that qualitative technique where you get together a group of experts, except you don't actually get them together. You keep their identity secret from each other. You ask them a question and compile reports and distribute reports and get consensus. Okay, all of this is trying to harness human intuition. Linear regression is a classic example of a technique that harnesses past data. So it's not qualitative, it's quantitative. All right, next question. Which calculation would reveal the bias in a forecasting technique? The mean error, or known as ME, or the mean absolute deviation? Mean error, also known as ME. Right, mean error just means the average of the errors, and we have commented that that is actually a lousy measure of accuracy because it allows positive and negative errors to cancel each other out. Ironically, that makes mean error a very good measure of bias, because if you let the positive and negative errors cancel each other out, you just average them, it's going to reveal if you tend to guess more to one side versus the other, and that is a bias. All right, next question. To calculate a forecast's percent error, the forecast error is divided by what? The actual. To calculate an error, just the plain error, we already said that. It's actual minus forecast. To convert it to a percent error, you take that actual minus forecast and then you divide it again by the actual. All right, last question. Assuming the same set of data is used in their calculation, which will always be smaller or perhaps equal, rarely, the correlation coefficient or the coefficient of determination? Well, the answer to this is that one, the coefficient of determination. But maybe we should pause and discuss why. Correlation coefficient. Remember that particular statistic is symbolized with, actually it's a rho, but it looks like a lowercase r, right? Okay, that's the traditional symbol of the correlation coefficient. The correlation coefficient is usually called by name. Now, this thing called the coefficient of determination, all right? Give me a minute while I write that whole thing out. Coefficient of determination is not referred to by its full name very often because it is rho or r squared. Usually instead of saying the coefficient of determination, we refer to the r squared. Oh, because it is the square of the correlation coefficient. Okay, these two things are related. This one's a square of the other one. Now you're thinking, no, wait, you just told me that the coefficient of determination would be smaller, right? But you're saying it's the square of the other one. Yes. Remember that the correlation coefficient is going to be some kind of fraction, right? Like a decimal. Oh, so if you take a fraction and you multiply it by itself, squaring it, it's going to create a smaller number. So that's how we know that generally the coefficient of determination is going to wind up smaller than the correlation coefficient.